So this is our last lecture in vapor power cycles. We've covered a lot of ground. We finished out the Rankine and then modifications for enhanced performance. So to increase the thermal efficiency of the plant, you'll have typically superheat coming out of the steam generator. You'll have reheat going back for at least one reheat in a real power plant. You'll have different types of feed water heaters. You could have more than one type of feed water heater. Today I'm going to talk about efficiencies. This is just a review of what we had in Thermo 1, but we want to talk about it because I've avoided having pump and turbine isentropic efficiencies. Up to this point, I assume they're 100%. So it's reversible expansion through the turbine as well as through the pump. It's just extra steps and extra work when you have the inefficiencies or the less than 100%. We'll talk about organic Rankine cycle because it's out there in the literature and kicked around and you may hear about it. Binary vapor power cycle, it's things that are kicked around, discussed, maybe not as popular or as common as others. Cogeneration, definitely kicked around, talked about. It's in our textbook, all these topics in our textbook as well. Clean coal or a combined cycle, integrated gasification, combined cycle type of power plant. I'll talk about that, especially how CPS Energy had almost bought into one of those power plants, clean coal. And then talk about where you can go to the internet if you want to learn more about steam traps, learn more about feed water heaters. I was going to play some videos, but we just don't have time. Excellent videos, excellent learning resources about the whole animation of a whole power plant or the steam turbine itself. So this is a long problem right here. And in this problem, you may get something like, oh, the isentropic efficiency of each turbine is this much. I'm not going to work this problem. I'm just going to step you through how you would handle that new piece of information. As well as, oh, the isentropic efficiency of each pump is 90%. What's a good strategy for now? What do I do when I'm given this added information in a long, complex problem? Well, probably analyze it with the TS diagram. So let's assume that we had this is a state going into the turbine, state 1. And we're going to expand it from this pressure, this line of pressure right here, to a much lower pressure. Maybe we go all the way down to this pressure line, which is 1 megapascal. As I've sketched it, it looks like if it was isentropic, it would be very high quality steam. True? And so this is what we would call state 2S, and then we would have another state which is our actual enthalpy, our actual state 2. And we've talked a little bit about this because the second law, if you do have some irreversibilities, then what is the exit entropy? It's higher, isn't it? It can't be lower. And so the actual state may still be in the two-phase region. It may actually come out saturated vapor if it just luckily lands right on that point. Or it could come out superheated. You're going to have to check. All right? Let's say that you came out at this pressure right here, 2 megapascal instead of the 1 megapascal. Well, it looks like even if it was isentropic, it would come out in the superheated region. And if there were any irreversibilities, it would just make it further away from the dome. It would just be out here. But if you have where state, let's say 2S is in the two-phase region, there's no guarantee that 2 actual is in the two-phase. It could be in the superheated region. Okay. So we recall our basic equation for what is the isentropic efficiency of a turbine. I like to break it into simple steps. So we have the work that you could get out of the turbine per unit mass going through the turbine. And if it's isentropic, that's going to be a larger amount of work per unit mass. Then the actual work out. Does that equation make sense? You go back to Thermo 1. Yeah, it's going to be 90%, 85%, something like that. And so what is the work, the turbine, if it's isentropic expansion? That would be the inlet enthalpy minus the exit enthalpy assuming isentropic expansion, so H2S. And H2S is gotten by a property evaluation where you're just looking up enthalpy as a function of the exit pressure of that steam turbine and the entropy, where the entropy is equal to the inlet entropy, like S1, S2 is equal to S1. That's isentropic expansion. So think about, how do I get H2S? It's a property evaluation, knowing two other properties, P and S. All right. So what you do when you're given this piece of information, I like to, first of all, calculate H2S, then calculate the work of the turbine if it was isentropic, and then finally unravel to calculate the work that the turbine actually produces, which is a fraction. The efficiency is the fraction times WTS, if it had been isentropic. So, you know, you can think about some numbers. Maybe this would have been 500 kilojoules per kilogram, and this is 90%. Well, then you're not going to get 500 kilojoules per kilogram. You'll get 90% of that, which would be what? 450. So think about numbers when you run through this. So now I would have the enthalpy. I could now calculate the enthalpy of 2 actual. Well, isn't that what energy content I had in the steam coming in, the enthalpy coming in, and then I subtract out WT actual. There you go. Now maybe I'm interested in locating, you know, the temperature 2 actual or the entropy 2 actual or whatever. Maybe on a TS diagram I want to know where its temperature is or where the entropy is of state 2 actual. Well, that's just a property evaluation. Find the temperature as a function of the pressure, P2, and the enthalpy, H2 actual. You get really good at property evaluations, don't you? Oh, now the two inputs, two independent intensive properties that are given as inputs are calculated, I can use that to get the other property of interest. Likewise, its entropy is a function of pressure and H2 actual. So you could do a good job of finding that actual state 2 somewhere on a TS diagram. And the type of line that is traditionally drawn is a solid line when we have reversible expansion through a device like a turbine, and a dashed line down to state 2 actual, the dash indicating it's not reversible. There are some irreversibilities. And the pathway is not exactly known. We just do a dashed line. Yes, sir?
So would state 2 and state 2S be at the same pressure?
Yeah, that's why I drew either this pressure right here or this whatever. I had 2 examples of changing pressure, but right. So this is, you're asking me why I don't have a subscript 2 right there? Well, I had 2 cases. I started with the blue and then I went to the green, indicating that sometimes the exit enthalpy or the exit state of a steam turbine could be superheated. That's why I switched and said, now, what happens if you come out at 2 megapascal? You're probably going to come out superheated, even if it's isentropic expansion. So let's get rid of that extra pressure line and just draw it like that. So yes, these 2 actuals, these 2 actuals, these 2 actuals, these 2 actuals, they all have the same pressure. In this case, it's all 1 megapascal. Sometimes I don't understand the student's question very well. Sorry if you asked me a good question and I flub it. Did I mention that already? I should have mentioned that earlier in this semester. But don't give up on me. Keep trying. All right, now, is that good for the turbine? Let's talk about the pump. So you come down, let's just think about the pump. How about the TS diagram? Should we draw it all in the TS diagram? Only if you have a magnifying glass, then you can zoom in right in there because it's all tucked in there, isn't it? So what you do is you say, for the isentropic efficiency of the pump, it's going to be the ratio of the work. Now, I'm going to work with a positive quantity. I want to work with a positive. When I do it in calculations for the cycle, and I know that that's a work not out of the pump but into the pump, then I'll put a negative sign, so I just add them up and not that the signs take care of themselves. Hopefully you've done that, but I'm going to talk about the positive work into the pump. All right, and the isentropic is less than the actual. Just compare. Here's our turbine. We had the work out of the turbine isentropic, work out of the turbine actual. It looks like they're in the wrong position. When you study turbines first, you say, oh, you're actual over isentropic. Then you go to a pump and you say, why is it now isentropic over actual? Well, you want an efficiency less than 100%. And so it's going to require more energy to achieve that pressure increase. So that's why it looks wrong the first time you see it. Maybe remember that in Thermo 1. It's like, I think that's a mistake there. No, it's actually that. That's correct. And so now you think, okay, well, what's the equation for the isentropic work? There's two ways of doing it. You can do it just like the turbine. You can say it's going to be the H. Maybe I should use different state numbers. What state number should I start at and then end at? Should I go 1 is the inlet and 2 is the exit, or is that too confusing? Is that okay? So 1 is the inlet to the pump, and 2 is the exit to the pump, which will be right there on a TS diagram at a higher pressure. So it'll be the, and I'm going to talk about the positive work. So it'll be enthalpy 2 isentropic minus enthalpy 1. Or you could do V sub F P2 minus P1. And we use this a lot. This is approximation. That approximation is really good because the water, the liquid water going into the pump is essentially incompressible. And for a modest pressure change, it's really good. All right. This one, trying to get H2S in table A-5 in our textbook. It's some interpolation. Table A-5 is really for high pressures, and so you can have some interpolation error. And so this approximation is used quite often in our textbook. But if you really go to a high pressure, use table A5, because that approximation breaks down at high pressure. You know, really go up to a couple, like 10 megapascal. Go way up there. So, so I try to caveat that. This is fast, but approximate. It's pretty accurate if you have modest pressure changes across the pump. If you have high pressure changes across the pump, go use table A5. Professor, what happens if I just always use table A5? You won't lose any points. On this problem right here, actually, I'm going to ask you always to use table A5. Okay? Just because there's some high pressures for some people. Maybe you get some numbers where it's not high pressure, but your neighbor does. So everybody just use table A5. Okay? And so you just have to interpolate in there. So how would I get H2S? Well, it's the enthalpy, knowing it's compressed liquid, at that high pressure, and at S2 equal to S1. Just like the turbine. Right? Okay. Let's continue on then. So what I do is I would calculate the H2S, calculate the work that would be the minimum work required to run that pump if everything was reversible. And then I would calculate the work. Actual is 1 over the pump isentropic efficiency times the work isentropic. Again, the first time you see that equation, you think, oh, why is it multiplied by the efficiency? Well, it's divided by. It takes actually more work to run the pump, not less, because of irreversibilities. And then it's the same type of algorithm. You say, okay, once I know the actual work in, then the actual enthalpy is the inlet enthalpy plus the work that actually went in. And then if you wanted to, you could say, well, what is the actual temperature to actual? Or these are optional, these are typically optional questions. Often you just need the enthalpy and you're done with the energy analysis. But you also have some optional questions like what is the actual exit temperature, or what is the actual exit entropy? Well, you would just say, I need to look it up as a property, knowing that pressure and knowing that enthalpy. And look up the entropy as a function of pressure and enthalpy. More time spent in table A4 or A5 doing the interpolation. Well, you'd have a long problem, and now if somebody gives you the efficiencies of a pump or a turbine, you can do it. It's just more steps. Okay? All right, more steps. Okay, are we ready to move on? Let's talk about working fluids. You do not have to use water as a working fluid in a vapor power cycle. It's just that water is a great fluid and is used in the vast majority of vapor power cycles. It's an excellent fluid. It's not a mediocre fluid. It's not a substandard fluid that we just use because of whatever reasons. No, it is a good fluid. It's hard to beat it. It's cheap. It's non-toxic, it's stable, it's plentiful. You can have a spill and the EPA is not going to come out. I could drop a gallon right here on the floor. Now the janitors wouldn't like it, but if I dropped a gallon of mercury, I'd be in big trouble. True? Have a big spill like that, or other fluids. They have great thermal properties. You can't underestimate. Good specific heat, high HFGs at reasonable pressures, a good thermal conductivity to move heat in and out of that fluid as it flows in heat exchangers, good density. I don't have to move a large volume to move a large mass. It's really a dense fluid. So a lot of reasons to use water. But what else? What else could you use in a vapor power cycle? Well, you'll see the kicking around of this organic Rankine cycle. Basically, it's still the major components of a boiler, turbine, condenser, pump, part of the Rankine cycle, and you can have enhancements to it like superheating, reheat, and feed water heaters. But this word organic means that you're basically using a organic molecule, typically they're high molar mass molecular fluids. You say, what does this word organic mean? It has some carbon in it. Does water have carbon in it? Is water an organic? No, it's not. You go back to like organic chemistry. Okay. So, what types of fluids might we use? Actually, refrigerants. They have typically some carbon in them, so they're organic fluids. You mean the refrigerants like we use in our air conditioning systems? Yeah, exactly. That's right. And why would you choose to move away from water, which has great properties, to a refrigerant, just so you could call it an organic Rankine cycle? No, well, because it changes at a different boiling point characteristics, different relationships between the temperature and the pressure in which it changes phase, where the dome sits. And so these are often used when you have a low temperature heat source. You burn coal, you can get it too hot, right? We have to cool it down and make sure it's not too hot, the steam going into our turbine, because the turbine materials can only take so high a temperature. But if you're coming from trying to use geothermal well to make some power, which they do have running in the United States as well as other places. So they have hot fluids down below the surface of the earth, drill a hole, tap into it, bring it up, put it through a power cycle, get some heat out of it, push it back down cooler than what you brought it up. Geothermal wells. Their temperatures are pretty low compared to what a coal plant can run at. Or maybe you're going to burn some industrial waste or trash or biofuels. Let's say you're going to burn some wood or paper products, or off a farm they leave a lot of the organic material out there on the farm fields, but they could collect it up and then propose, many people have proposed, burn that in a power plant instead of coal or natural gas, and then make some power. Maybe burn some sawdust. I've seen that. Or other chips. So a lot of things have been kicked around. I even saw where a company from France was going to come in to South Texas down by Corpus and harvest mesquite trees. And they're going to chunk them up, put them on big boats, send them all the way to France, and then burn them in France because, see, that's organic. And it would be carbon neutral, no CO2 penalty or tax. Because it's CO2 is right there. It's not digging it out from underneath the earth and then adding it to the atmosphere. Anyway, so lower temperature is what motivates these. There are some excellent videos, and you can see how they operate. People would have to design them, and engineers have designed them, and you can go buy them, or companies can buy them. Typically, they want to figure out how you're going to get that heat into the working fluid. Here in this video, if I watched it recently, they basically have a burner, and they heat up oil, and then they pass oil over. Hot oil comes into the cycle, and then that oil is used to boil or evaporate, if you want to call it that, but it's really boiling a refrigerant in an evaporator. And I've seen where they have taken compressors and tried to run them backwards with small modifications, things that are typically in the air conditioning, refrigeration business, and adapt it for power production. Okay. Didn't have time to go into that. But one of the things that I would like to explore is, let's take a look at our favorite temperature entropy diagram drawn to scale for different fluids. I'll show 3 fluids. The first one is refrigerant 22. That's an older refrigerant. It's been phased out. 20 years ago, you could find it in a lot of places. You may still have it in a few of your home residential air conditioning systems. R22. 12 went out earlier. 22's on the way out. But if right now we have a lot of 134A and 410A is out there in use. Anybody know if they have a system using R22? Nobody does? A few years ago, people would have raised their hands more. Okay. But this is a property diagram. What do you see right here? It's a dome. So we can get that refrigerant, R22, in a 2-phase liquid vapor mixture. Right in here, this whole region is a state of compressed liquid. Out in here, superheated vapor. This is all kind of supercritical states. It's above the critical point. And that's what about out here, Professor? That's no man's land. You just really don't get refrigerant 22. It would be extremely high pressure. These are kicking up high pressures. To get the point out here, you'd have to have super high pressure. Just don't even plot it. It's no man's land. Okay? So this is very familiar. You know it for the steam. We've focused on the steam, but you can also look at a TS diagram for R22. Now, what I did was I thought, well, maybe we have to reject heat at a certain temperature. If you ever reject it at ambient temperature, you reject it at around 300 K. So think about it. I'm going to have to throw heat out of the power cycle at 300 K. All right, so I put this on the Kelvin temperature scale. There's 300 K. So if you're going to be condensing it and maybe cooling it with lake water or some other ambient fluid from the environment, basically I can tell you roughly what the condenser pressure is going to be. I'll just find this pressure that kind of comes in that vicinity of 300 K, and I think I rounded it off, and what does that say for pressure? About 1.1 megapascal, 1 megapascal. If I have to reject heat to the ambient, that really dictates my condenser pressure, doesn't it? Now, let's say we don't have a very high temperature heat source. Maybe it's only 100 degrees C or 100 K higher, which would be only about 75 K. So maybe it's 400 Kelvin. What did I just say? 75 degrees C heat source, which is about 400 Kelvin. So here's my high temperature heat source. Well, I want to bring it out of the evaporator or boiler at 400 Kelvin. As a design engineer, what pressure would I like to bring it out at? let's say I decided to bring it out at this pressure right here. Well, I'm kind of walking you through a design choice, right? Wouldn't that be where it comes out at that temperature and pressure? Now, if I put it through a pretty good expansion through a turbine, and I can't drop it, I cannot drop it below that pressure. Why? We just had that discussion. That's my condenser pressure. Where is the exit state going to be? Here, or maybe if I have some irreversibilities, it'll move up. Is that a good design choice to bring it out at this state? No. It's superheated still. The first thing I'm going to do is it's going to be pretty warm. And the first thing I'm going to do, try to move it through the condenser, I'm going to cool that superheated vapor until it gets to the point at which it's going to start to condense down near 300 Kelvin, and then I'm going to condense it. That's not a good design choice, is it? So what's my better design choice? Should I maybe bring it out at around this pressure, which is, what's that pressure? About 5 megapascal. Yeah, if I bring it out at around 400 Kelvin, 5 megapascal, and I expand it, doesn't that look a lot better? Yeah, that looks a lot better. What I think I did was I looked at the quality at the 300 at that low pressure, and then I said, let's just move up and find the pressure at which the temperature of 400. So it's like this is constant S at that so as a function of S and T, I found that, it's about 5.3 megapascal. This is a little higher than 5 megapascal. That would be kind of optimal. You bring it out at about 5.3. Somebody says, I learned that the boiler pressure should be taken up and go as high as possible, right? Okay, let's do that. Let's not bring it out at 5.3. Let's take it out at 9 megapascal. We could do that. Okay, if you brought it out at 400 Kelvin and 9 megapascal, where would it be on our TS diagram? Is that going to be good for the system? No. Because if you expand it, you're going to be trying to expand a thick, soupy, two-phase mixture for the majority of the time right in here. It's not good for turbines. It's not going to work. So in this case, no, we need to sort of stop it. We need to have it only up to about 5.3 megapascal. And there's, see what we're doing? We're just doing conceptual design for that refrigerant. What would work? I need the refrigerant at this pressure in the condenser, this pressure in the boiler, and it's dictated by property values. All right, let's take a look at another one and do the same thing. This is a different refrigerant, R11. Okay, look at the shape of that dome. What do we notice about the dome? It's very steep, very steep. So it's not as symmetric, and so it's very steep on the saturated vapor side. So if we do the same thing, we say here's 300. We have to reject it in our lake water or other things. And our energy source is 400. Okay. One of the things I forgot to point out back here, most of the time, if you look at this refrigerant, if you really have a heat source at 400, you're going to be supercritical. Yes, if you had a pressure of only 1 or so right in here, you would go through a distinct phase change of boiling or evaporation, where there was definitely liquid and vapor, and under the presence of gravity, liquid sinks to the bottom of my container, where then it generates bubbles and pops out. That's boiling. You know what I mean? Okay. But if you're running up here at the higher pressure, what did we say that was? About 5.3 megapascal. Look at this. Does it go through the dome? No. You won't have a distinct phase change in that system. Or if you even went with the higher. So it'd be like a supercritical cycle. All right. But in here, for this refrigerant, you're definitely going to go through the phase change. So let's take a look. Let's say I want it to come out right here because of the 300 Kelvin temperature I need to reject heat to, and I want it to come out saturated vapor from a design principle. That's great. And it's going to come out of the turbine because my heat source is limited to 400 Kelvin. If I come up straight up thinking backwards, I could probably run with a pressure a little above 1 megapascal, and it'd actually come out very barely superheated, right? It'd actually come out very close to being saturated vapor. And that's what we find, is that if you take a look and say, okay, I'm going to start with this low temperature, this is my entropy, do an isentropic kind of backward look at it up to this high temperature, it's slightly superheated, but it's pretty close to the dome, and it's at about 1.3, this is 1, this is about 1.34 megapascal. Actually, that's pretty good. It's actually because a lot of that heat is being brought in close to the high temperature source from our Carnot studies. That's great for performance, isn't it? Not a whole lot of superheating. I mean, a lot of the heat's brought in there. You could work with the cycle down here to improve efficiencies with feed water heaters and reheat, but let's leave that alone. You can even go and find a fluid, isopentane. Take a look at that slope. It's actually backward. It actually helps it stay dry, very, very dry in the expansion. We come across at 300, come across at 400. You would be looking at it, you'd be saying, if I wanted out here, wow, I could even start the expansion earlier. Or here, it's definitely going to come out like that. Maybe it's too dry for your design purposes. So, I mean, right here, if you wanted to come out here, you'd actually start right in here. The theory would say, oh, you could start expanding when all of it hasn't even boiled. That's probably not good to start expanding at 70% quality. So it would be better to pick maybe a fluid that has a characteristic this is very steep in there. Well, I wish I had more time to explore these type of design considerations. Basically, you're mastering in this class the ability to make the calculations. Hopefully you think about the calculations and the implications. All right, let's talk about the binary vapor power cycle. It's in the textbook. First of all, no problems on this test. No problems on the final for the binary. No problems on the final for the organic Rankine cycle. This is just more for your general edification. Hopefully you come out of the class. So easy lecture, right? It's like sometimes I should say, this is not on the test. Then he says, yeah, that's great. That's my favorite question. Is this on the test, Professor? You know, what are we talking about here? All right. So binary, it's meaning two. So basically you have a vapor power cycle and then another vapor power cycle. And one may be running with a fluid that works at high temperatures, and maybe you use an organic Rankine cycle or some other fluid that works at lower temperatures. And right in here, you'll have a heat exchanger, and that heat exchanger will act like the condenser for the higher temperature vapor power cycle, and it'll act like the boiler in the lower temperature vapor power cycle with a different fluid. And you would have the turbine for that one. You'd have a turbine for this one. You'd have a condenser for this one. Here you'd have a steam generator or boiler for this one. You'd have a pump. You'd have a pump. And so you do have four major components. It's just that one is shared between the two. This heat exchanger is the condenser for one and the boiler for the other. Are these that popular? No. But we should be able to, if you wanted to, you could propose it and work on it. Do I know of any of these in operation? No. Okay. How about the organic? Yes. Yeah, there's companies making them and selling them and plants running them with the different refrigerants as the working fluid. But this is neat conceptually. So let's leave that alone. You could then calculate work out here, work out there, and do a bunch of analysis on it. Cogeneration. What does that mean? Co meaning something like you're doing two things of use. So you're going to make some electricity as well as you're going to use some energy for some good purpose. Now, in a winter, we need heat for our buildings. And so that's what is proposed. So you could have a power plant that runs, and it could make electricity, and it could have the ability to divert some of the steam before it's expanded way, way down at low pressure still, some intermediate pressure, still have some high temperature, and you could put it through a heat exchanger which would heat up some steam that would then go and circulate to buildings and provide some heat to a series of buildings, maybe in a downtown environment. These are very common in major cities. Is San Antonio a major city? Yeah, we did have one. Okay, but how long are our winters around here? 2 weeks. How long are our summers? 11 and a half months. So basically, we also have, when we get to the refrigeration, we have a chilled water loop. So a lot of these plants will have a chilled water loop, and then they'll have a steam loop. And so a building like the Marriott or the Henry B. Gonzalez Convention Center or the big, where they have the games, what do they call that? Alamo Dome. Sorry, I don't know why I drew a blank on that one. Basically, they're all in the loop. The federal buildings downtown, Hilton's, the Marriott's, all those hotels are all in the loop. And they use the chilled water. They definitely use it. And about 5 to 7 years ago, they were pulling steam out of a loop. Okay, it's not run by CPS, it's run by SAWS, our water company. It goes back to the beginning when they had the convention, the World Fair in San Antonio. That's when they said, we need this. They approached CPS. CPS said, we don't want any business in that. They approached SAWS. SAWS, we'll do it. And that's why SAWS is in that energy business and not CPS. It's just historical quirk. Okay? It should probably be CPS. They did have the steam loop for a while, and then what the engineers did was they ran the numbers and they said, we're making good money on our chilled water loop. We're losing money every day we run the steam loop. And so they basically told everybody that's on the loop, they said, you have about 3 to 5 years to make the changes, but we're shutting this down in about 3 to 5 years. They had to give them long enough notice, and then they basically brought it down and shut it down and disabled the boilers and chopped them up and took them out and made room for more chillers. They actually moved, they have 2 chiller plants down there now because of the number of buildings and square foot they serve. But this is very used in bigger cities up north where they have a significant winter. And it makes sense. So on moderate days, they don't need a lot of heating for a lot of the buildings. Just as very little goes this way, and you may just make electricity. Doesn't this make sense? Yeah, and engineers design it and run it. Now we talk about another topic, carbon dioxide. This is a big topic. When I was taking a class like this, it wasn't even mentioned. It wasn't even mentioned. And now it's mentioned. And you can't hardly listen to the news with one day, 1 week without some impact of carbon dioxide in the environment. I just heard the article, maybe somebody heard it. It was about how CO2, a lot of CO2 ends up being absorbed in water, and then it gets absorbed in our oceans and lakes and things like that. And the ppm just creeps up a little bit, but it can change the acidity, the pH, just a little, because of environmental increase in CO2 levels. And I just heard an article how it's having a huge impact on some industry. Anybody heard that article? I forget what it was. Some crabs or snails, I don't know, clams or some fish. Just a very modest change in the pH in some estuaries, and then they were seeing that impact. You're going to see more of that in your lifetime, so get used to it. Where do we get a lot of CO2 pumped into the atmosphere from? Burning coal, making electricity. That's going down, but it's not going to zero anytime soon. Well, we're going to move to natural gas. What's natural gas? CH4. Where does the C in the methane go? Carbon dioxide. Oh yeah, it's a lot cleaner, but it's like you cut your electric bill in half or so. You didn't zero out your carbon dioxide emissions, you just maybe cut it in half. We'll get to that later. But you didn't zero it out. Oh yeah, it's clean. But you still got a lot of CO2 going up in the stack. Anyway, so people have been looking, and engineers have been tasked for reducing the emission of CO2 into the atmosphere. Well, if you're going to burn something like natural gas, it's going to produce CO2. What are you going to do with it? Basically capture it and then put it somewhere where it won't escape into the atmosphere. So you'll see that word capture, sequestration kicked around. And maybe put it to some useful purpose somewhere. Well, about 10 years ago, that was more kicked around. And when we get to the gas power cycle, we'll have a combined gas vapor power cycle, and they'll still have coal as a primary fuel, but they'll try and make it cleaner by first gasifying the coal, making it like a natural gas. You can clean up a lot of the emissions out of it. And then after that power plant, try to capture the CO2 and do something useful with it. Anybody may have heard more about this a few years ago. This was a hotter topic. But this website's still up and running, Texas Clean Energy Project, Texas Clean Coal Energy Project, really, if you want to put it in there. But coal is bad, and so for PR purposes, we take it out. It's like the South Texas Nuclear Project was renamed. Instead of having 4 words, South Texas Nuclear Project, they are now 3 words. 1 was deleted. Did they remove South? Did they remove Texas? Did they remove nuclear, or did they remove project? They removed nuclear. It's the South Texas Project. So basically, we have clean energy now, not clean coal. But anyway, this website, you can go take a look at it. They're going to build this thing, this power plant, way out here in Penwell, Texas. When I heard about it, I said, where is Penwell? I have no idea. Anyway, here's San Antonio. Here's the border with Mexico. That's El Paso. This is Fort Worth. There's Odessa and Midland. And look where Penwell is. You say, why does anybody in San Antonio care? Because you almost bought into it. CPS Energy said, great idea. We're going to bankroll it. We're in. We want part of that action. CPS Energy. You're the owners of CPS Energy if you live in Bexar County, essentially. Okay? So CPS Energy bought 200 megawatt commitment of the power out of that Texas Clean Coal project. This was dated 2012. I know it's a few years old. I'll bring you up to date. And it was going to have a total of 400 megawatts. So if you're going to buy 200 megawatts of the 400, what percent owner are you? You're 50%. You own basically or want 50% of what it can produce. It's not cheap, but they had a price tag of $2.4 billion at some time back then. It's going to do the carbon capture and storage. That's why they put it in Penwell. Let's go back and look at the map. They could do something with a whole bunch of CO2. They could stuff it down into the ground. Why would they want to stuff it into the ground out by Midland, Odessa, maybe not out by Bernie or down by Floresville and Poteet or whatever? Because the Permian Basin. And at the time, 10 to 15 years ago, when these ideas were kicked around, that could stimulate more production of oil out of a field that's slowly on the decline, right? So you pump down CO2 and that could stimulate and get more oil out. Ha-ha, that's a win-win. So that's why they proposed to burn coal out, let me go back here, in Penwell. It's not like more people are living in Penwell. You know, population's booming, you know, we need megawatts of electricity. No. People are booming over here in Dallas, Fort Worth. They're booming in San Antonio. The population's going up. Booming in Houston. There ain't much change in all these other places. It just isn't. It just isn't. It's not like, you know, maybe El Paso's experiencing some rapid growth in its population, but it's not like they need power out in Midland, Odessa. It's just so they could put it down in the ground, pump it down. All right. CPS said, great idea. You may have heard of this little thing, the American Recovery and Reinvestment Act of 2009. I know you're probably still in kindergarten. What happened in 2009, the American Recovery and Reinvestment Act? Obama's first year in office? Stimulate the economy? We're going to invest money. And they got 211 million out of that one. I don't know where it got spent, but I guess it stimulated some things. I'm just sharing that money went there on the 2.5 billion or 2.4 billion. So what happened? Oh, they were getting permits from Texas Commission on Environmental Quality. Things were looking good, moving along. This is going to happen. And then what happened? CPS Energy purchase power agreement with Texas Clean Energy Project expired on December 31st. This is 2014. Doyle Beneby, I think he was the president at the time, said, we don't want any part of it now. Things have changed. What changed? It's that smiley face in South Texas. Goes along the border. That a lot of mechanical engineers graduate from UTSA have landed careers in when it was hot, and then they dried up. But now they're actually going back to work. And probably some in this room will end up working in that. That's the smiley face of the Eagle Ford Shale. And Doyle Beneby said, we got so much natural gas right under our own feet. Thank you, coal, but we don't need it anymore. So we're out. You didn't meet your commitment on some deadlines. Boom. We got the option to get out of this project, and they're now out. So you don't own it. You haven't bought into it anymore. I don't know the current status of that project, but they went out. So in the time, then they put the start and ideas on paper and bringing it in design. Basically, fracking and cheap natural gas just changed the market completely. That's what happened. All right, so I try to bring you up to date a little bit. I could spend some more time talking about nuclear power. CPS almost bought into more power there. I actually went to the mayor's office. The mayor killed it, Castro at the time. But let's not talk about that. Also, the nuclear renaissance was kicked around, but it went down with the price of natural gas as well. So if you see the price of natural gas go way up and other things, you'll see people looking again at coal, looking again at nuclear, looking again at clean coal. But right now, it's all natural gas. We're just all excited. We're just building natural gas plants left and right as a nation, but nothing else. All right, I encourage you to take a look, especially when you take heat transfer class. You can think back, you can look more and study more about what's happening in these feed water heaters. They're just big heat exchangers, but they can have a superheat and then a two-phase region and a subcooled region. And there's a lot of engineering design in those, and there's some really good videos on them. Also, steam traps. I mentioned this. Actually, and some engineers that are out there in the field, they really understand steam traps. Some don't. And you can have malfunctioning steam traps, and they're really hard to detect. You really need to. And so what will happen is the steam trap will let vapor through when it should only let liquid condensate through. And people will diagnose them with ultrasonic sound measurements on them, and they're pretty neat devices. They're old school. They've been around for a long time. But if you're going to work in steam, you should know about steam traps. And there's a number of really good videos on how they operate, how they work, and how they fail. Also, there's some great videos that have been put out recently that dovetail perfectly. I was going to show them, but they take 10, 15 minutes. I just encourage you, go find them. It's how a power plant runs. It's 7 minutes. And how does this work? And so they'll kind of zoom you through. Over here would be the boiler. And that's maybe the coal pulverization and what it looks like in the firebox and the tubes and this heat exchanger here and there. And then steam comes over at this pressure and temperature, expands through the high pressure turbine. Maybe goes back for reheat. Maybe goes to the intermediate low pressure turbines. There's our electric generator. Overall thermal efficiency. This is what we've been talking about, right? Yeah, so instead of just pieces of paper, you might find these very helpful to understand what's going on. Even just talking about superheating and the boiler and how it works. Well, with that, I wanted to cover some of these fun topics. They're not on the exam. But let's say you want to go work for CPS Energy or one of their plants or something. You know, if I was interviewing you, or think about if you're going to be hired in a plant like that, you would just probably not talk a whole lot about show me how to make an enthalpy calculation and look up a value in a table. But what do you know about power plants? What do you know about the challenges associated with emissions? What do you know about how to improve efficiency. And these softer topics will come up in interviews. With that, I thank you for your attention. Let's now talk about our exam.